Thank you very much for the invitation to speak here. So I'd like to talk about harmonic maps, unitary representations, and random matrices, and how these three kind of objects interact with each other. So since I'm not exactly in the main theme of this conference, I mean, not exactly, I thought I would introduce a little bit slowly what I'm going to talk about from the point of view of my subfield, which is geometric analysis. So in geometric analysis, there are a lot of situations where you're interested in some geometric functional that's going to be defined on a set of objects. So by the way, I'm preparing some lecture notes. They're under constructions, and they're on my website, if you're interested. So here's the cartoon picture I like to draw. What you often have is a functional. You can think of the functional as a way to measure the size, maybe of your object. Maybe it's a notion of energy, of area, or volume. And so it's defined on a space of objects. And you want them to satisfy some constraints C. So here, as objects, you can imagine maybe surfaces or a set of manifolds. And as constraints, you can think of, for example, boundary conditions, or maybe a symmetry condition, or maybe a curvature bound condition. All those fit in this general framework. And so what geometric analysts like to do is to come up with interesting notions of size, so come up with a functional, and they're very interested in those objects. So the either minimizers of the functional or more general critical points of the functional. So if you think of harmonic maps, what I'm going to talk about, or minimal surfaces, Einstein manifolds, G2 manifolds, a lot of nice special geometric objects can be thought of as critical points of natural functionals. And the traditionally interesting questions you may ask are these minimizers, do they exist first? And if they exist, can you show that they're unique? So the rigidity part. So the main guiding question of this lecture is going to be a new, at least newer kind of question, which is the following. And it's going to be motivated by the fact that for most interesting choices of F and interesting choices of objects, you're never going to be able to explicitly or completely describe the geometry of the minimizers of F. So here's the question. So what is the geometry of minimizers and their typical constraints? Here the keyword is typical. So you want to study, try to understand the shape or the geometry of minimizers if the constraints are chosen maybe at random or at least in a typical fashion. So this is not something completely new. For example, in dynamical systems, in some sense, you already have a lot of results for this kind of questions, say if you're interested in closed geodesics or geodesics in general in negatively curved manifolds, and you want to know something about the random choice of geodesics. So this is exactly the same kind of questions, but in a more geometric analysis perspective. So let me tell you the specific choices of F, O, and C in my lecture. So in this lecture, we're somehow going to focus on maybe this, one of the simplest settings that you can think of if you're looking at surfaces from a differential geometric point of view. So F is going to be the Dirichlet energy. The set of objects are going to be some smooth maps from surfaces to Euclidean spheres. And the constraints are going to be given by an equivalence constraint. So you will only consider maps that are equivalent under a group action by a surface group. Right, so let me say a little bit more about the Dirichlet energy before I continue. So let's say you have a Riemannian surface. And here you have another Riemannian manifold. Okay. So you can consider some smooth map from the surface to M. And well, the maybe easiest way to measure the complexity of your U is to look at its Dirichlet energy. So the Dirichlet energy is just defined as follows. So basically what you're doing is you're looking at the differential of your map, and there's a natural norm for this differential, and you integrate this norm square on the surface. So I'm not going to give the explicit definition here. I'm going to do it a little bit later. But I want to claim that this is really one of the most basic functionals you can think of. And in the case where M is the real line, the Dirichlet energy is the usual Dirichlet energy. So the minimizers of the Dirichlet energy are called harmonic maps, and they're direct generalizations of harmonic functions. So functions with zero Laplacian. Or more generally, critical points. Are harmonic maps, okay? And so now that we have this vocabulary, maybe I can tell you an informal version of the main result of this lecture, which is going to be that under random equivalence constraints, the corresponding special objects that you have, the harmonic maps, they're going to look more and more like another special object, which is the hyperbolic plane. Let's say with high probability, because I have the word random here. So the goal is going to make sense of this statement, but also it's going to be an excuse to introduce and talk a lot about some basic objects like harmonic maps, minimal surfaces on the geometric side, and unitary representations, and notions about unitary representations, like the representation of PSL to R, or the notion of strong convergence in random matrices. So I'm going to mention all of this, and it's only towards the end of the lectures that I'm going to really give some ideas behind the proof of the statement. So this is an introduction inside my introduction, so I'm going to get into more details about this statement. But let's see if there's any general questions.
Well, which is it? Minimizes or critical points above 4 what a harmonic map is. Critical points good enough?
No, so you really, for this kind of, for my specific setting, you need minimizers. Yeah. So let me give you an application of this kind of constructions, which is expressed completely in classical differential geometric terms. And here the background question is the following. So what is the best or most beautiful way to immerse a given surface inside Euclidean space? Inside some Euclidean space. And well, so usually I like specific questions, but sometimes it's nice to have those kind of very vague questions that are summarizing a lot of results in some specific direction. So here, part of the job, if you want, is to define what you mean by best. And let me give you some examples of notions of good ways of immersing a surface into a Euclidean space. Well, no. So before that, I'm going to give you directly the application of the main result. So that's done. So you give me any closed hyperbolic surface and also some epsilon strictly larger than 0. The claim is that there exists a finite cover such that you can map this finite cover in a very nice way inside Euclidean space. So psi is a harmonic immersion. And if you look at the pullback metric of this smooth map, it's going to be very close to a rescaling of the hyperbolic metric. So let's say in the C2 topology, what you can show is that the pullback metric has to be C2 close to this rescaling of the hyperbolic metric. So these are very nice because they are both harmonic and almost isometric. So if you have no questions on the statement, I want to give you some background on the, some classical results in that direction.
Any idea you can say why it doesn't 8?
Yeah, that's a very good question. So it appears with very high probability in this kind of result here. This is the coefficient that appears. And well, there are some a posteriori explanations for the 1/8. I don't have a very a short answer to your question. But I have a conjecture that if you have such maps, then, and if you have a coefficient here, then 1/8 is the minimum coefficient that you could get. You could get more, but you could never get less than 1/8 somehow.
Do you have any control on the bounds of the degree of the cover in terms of epsilon?
That's a good question. All I know is if you leave out any compact subset of, say, the moduli space of a hyperbolic matrix, then this degree has to go up. So maybe that answers a version of your question. Another version of your question is, OK, when epsilon goes to 0, how do these things evolve? And let me say that it's known that both the degree of the finite cover and the dimension of the sphere here, they both have to diverge if epsilon goes to 0. It has to be true. So in particular, if you fix the dimension and you're never going to, and if you fix the hyperbolic surface, you're never going to have such properties. Okay.
Does a random finite cover would make epsilon go to 0? Like, what do you expect with most random finite covers?
So that's a good question too. I don't know actually, because in the construction, those are not going to be random covers in the uniform for the uniform measure. Yeah.
Just to ensure, so you're normalizing the metric so that it has constant curvature.
Yes. Yes. For me, hyperbolic metric is constant sectional curvature -1. So I want to spend maybe 10 minutes explaining why this result is kind of sharp, kind of optimal. No. So let me give you some backgrounds. And also, let's assume that the genius of sigma is at least 2, because this is the generic case. It's, for me, more interesting than the sphere and torus case. So first thing, of course, best metrics intrinsically are the hyperbolic metrics. So I'm going, in this little discussion, I'm going to always assume that G0 is a Riemannian metric on sigma, which is a rescaling of a hyperbolic metric. So why do I allow rescaling? It's just to have a little bit of flexibility in my discussion. But so G hype, you take any hyperbolic metric you want on this surface. So in view of this question, and also the title of this talk, so one way to have a very nice immersion of a surface inside a space is to have a harmonic immersion, right? So this condition is a beautiful condition. If you've worked with harmonic functions, you know that they have a lot of very nice properties. Now, if you want to work with harmonic maps from a surface to Rn, you're a little bit in trouble because due to the maximum principle, you don't have any non-trivial such maps. So any harmonic map from a closed surface to Rn is going to be trivial. It's going to have a point as image. So that's just the maximum principle. So the next best thing you can do is to normalize the image and say that, OK, you want to impose the map to have image inside a unit sphere, say. So But then, and this has been known for decades, there are many, many different harmonic maps from this given surface to a unit sphere. Already when d is equal to 3. And let me give you some names.
You mean infinitely many or?
Oh yeah, infinitely many, easy, yeah. And there's been a lot of work on those surfaces, actually also a lot of work on a special case of such surfaces called minimal surfaces. Let me give you a few names. Okay, so those maps are extremely interesting, etc. But there are too many of them to be a satisfying answer to, say, our question of best immersion, right? Okay. So there's somehow too much flexibility in this context. By the way, maybe I'm going to mention later or tomorrow that when the ambient space here is negatively curved, then suddenly you have a lot of rigidity, and for harmonic maps, you have some kind of uniqueness statements. But this is not the setting that we're going to consider in those lectures. There's another way to think of that question, and you can say, well, a nice way to immerse, say, a hyperbolic surface is to try to immerse it isometrically. So let me remind you that because of Nash, the Nash embedding theorem, there's again a lot of such isometric immersions. And let's see. So in fact, you can start with any map which decreases distances, and you can perturb in a C0 topology this map to make it an isometric embedding in the sense of Riemannian geometry. So in that sense, it's way too flexible to be a good answer to the question, if you see what I mean. And this flexibility is also, so the reason why sometimes you hear that the Nash theorem is useless, things like that, is because of this overflexibility. Up. And yeah, so there are some nice pictures by the, I think it's called EVEA project. They have some nice pictures of isometrically embedded flat tori in R3, and you'll see that it's typically extremely folded. So the surfaces that you got, intrinsically, of course, they're nice, but extrinsically, they're extremely folded and not that nice. So probably you saw it coming. So now what happens if you try to combine the two, right? So maybe you want to combine having an isometric immersion with being harmonic inside a sphere. So by the way, the method of the proof here enables you to replace Rm by Rm by some sphere if you want. Okay. So what happens if you impose harmonic plus isometric? And so here you have the opposite problem. You have too much rigidity. There's no example. There cannot be any example of such maps. So the statement is that there's no map from the surface, the rescaled hyperbolic surface, to any unit sphere, which is both harmonic and isometric. So it's in that context that this statement is kind of optimal, because you cannot be exactly harmonic and isometric, but the statement is saying up to going to a finite cover, you can have the best, almost the best of both worlds. You can be exactly harmonic and almost isometric. Right, so any questions on that?
What is known about the higher dimensional case?
Oh, if you replace the surface by
Like three-dimensional hyperbolic.
actually, not much is known. So the Nash embedding stuff, it works for any dimension. But if you're looking at the higher dimensional, again, so this part is also very general. So there's a lot of harmonic maps. This subtraction, I don't know. Actually, it's probably true also, but the method of this proof completely fails.
And you don't know about the analog combination one?
No, of course, yeah.
If such a map exists, can't you just restrict it to a set inside?
What do you mean?
If it exists from a higher dimensional manifold to the sphere, restrict it to a set.
No, so this condition does not play well with restriction to a surface. And yeah.
And what is known about the two tori?
Two tori. So for two tori, or for the round sphere, this is possible to have something that's isometric and also minimal. So those are beautiful minimal surfaces. And you may have heard of the Clifford torus. This is a isometric embedding of the flat torus, of a certain flat torus, in a minimal way, harmonic way, inside a sphere.
And S2 is a trivial case.
Yes. Okay. I want to make some comments about the existence of those surfaces. So on the face of it, it's an existence, pure existence result. So I'm telling you that there exist such harmonic maps. But the first remark is that the construction is completely probabilistic. I have no way, no deterministic algorithm, if you want, to construct such maps. I can only tell you that with high probability, there's a way to obtain them, so they exist. But it's absolutely not clear geometrically how you would construct them in an explicit or even semi-explicit way. They're really obtained by the probabilistic method. And so this has to do with, in the proof, we're really going to use random matrix theory. Okay, so that's the first remark. And the second remark is that, at least in the setting of the main result, all the maps are going to look like that with very high probability. So in that sense, it's going to be a probabilistic rigidity result. So I think it's nice because the statement is completely classical, but the tools to prove that are coming from all kinds of fields, and in particular random matrix theory. Let's see. So now I want to state the main results, and I'll try to give you some kind of a plan for the next few lectures. So here's the setup. S is a closed Riemann surface. S tilde is its universal cover. And I'm going to denote by G hype the unique conformal hyperbolic metric on S. So I'm going to always assume that such a metric exists. In the next few lectures, I'm going to talk a bit about standard classical harmonic map theory. So it tells you the following. Sachs-Uhlenbeck, Shen and Yao. So the statement tells you that from an isometric action of a surface group, you can cook up a corresponding harmonic map. So you give me any isometric action of the fundamental group of S on the sphere. What you get using the variational methods that I mentioned is going to be a harmonic map from the universal cover of S to your sphere. So psi is harmonic. It's pi1 equivalent with respect to the action. Let me call it rho. And it's also equivalently energy minimizing. So being equivalently energy minimizing just means that your map, if you just look at the fundamental domain, your map is going to be of minimal energy among all the maps that satisfy this equivalence constraint.
And this only works for surfaces? Or?
So the existence theory is works best for surfaces, yes. I don't know if the same is true on the nose for higher dimensional manifolds. Yeah.
Is it specific to the sphere, or is it specific?
No, so I'm going to give you the general results later, but this is a very special case where the target space is a sphere. And I like to think of this harmonic map as the 2D shape, the kind of shape that you can associate to the representation or the action. So rho is a kind of topological object, and you get this 2D shape as a result of this procedure. And as I said, if you give me a general action of pi1 on a sphere, okay, sure, you get some harmonic map from some surface to a sphere, but you cannot say much more. And the hope is that maybe if you focus on the typical case, then you can say much more, and that's the statement. So what happens when the isometric action is chosen at random? Here, I want to talk about the concept coming from random matrix theory and free probability called strong convergence. So instead of giving you the formal definition, which I'm going to give you a little bit later in the next lectures, I want to give you some intuition on what strong convergence means or achieves. Okay, so first it's a property for sequences of isometric actions of pi1s, for example. Let me give you some intuition. So the intuition is that if you have a sequence of isometric actions of pi1s on a sphere, they strongly converge if, as you go deep inside the sequence, they become more and more indistinguishable from a canonical action called the regular representation. So that's going to be a consequence of the definition. So the regular representation is also something I'm going to define later. But it's a group action on an infinite dimensional sphere. So that's the first point. And the next point, which makes this concept actually interesting, is that it's universal in the sense of a probabilist, meaning for many, many different models of random sequences of such actions, this property is going to be true. So you have many ways to define random actions of a group. Let's say you start with a free group instead of a surface group. Then if your free group has rank k, maybe you can, so an isometric action is going to be determined by where you're sending the generators of your free group. And you can choose those generators according to some probability measure, for example, the Haar measure on the space of linear isometries, etc., etc. So you have other choices, and all the natural choices basically are going to give you this property that you're strongly converging. Right, so is there any question on this notion? That was a very vague introduction.
Sorry, the index of the sphere, so the dimension of the sphere here is changing as well.
Yeah. Yeah, so in this definition, you don't impose the dimension to change, but we'll see that it implies that it has to go to infinity. Yeah, I think it's one of the exercises. So there's been a lot of recent breakthroughs on the notion of strong convergence, and I'll just suggest you to read the surveys of McGee and also Van Handel if you want to know more about strong convergence beyond what I'm going to talk about. So here's the statement of the main theorem. That's going to imply, for example, the application I described earlier. So let's consider a sequence of isometric actions on pi1 on some sphere. And because of standard harmonic map theory, you get a harmonic map from the universal cover of S to your Euclidean unit sphere. And the statement is going to be, oh, maybe I shouldn't erase that because it's going to be this. The statement is that if this sequence of isometric actions strongly converge, then you know something about the geometry of those harmonic maps. So as you can see, the limit metric is uniquely determined, right? G hype, again, is the unique hyperbolic metric on S. The Euclidean metric here is just the standard round metric on the unit sphere. So what's interesting here is that, you know, in geometry, you have those two ways of thinking of optimal shapes. You have the extrinsic way, so harmonic maps, minimal surfaces, and the intrinsic way, you know, hyperbolic metrics, Einstein manifolds, and things like this. And in this setting, somehow they coincide somehow in the limit, which is something that might not be expected, right? Because here you're just solving an optimization involving the Dirichlet energy. You're pulling back a round metric, but somehow the limit is the hyperbolic metric. So what makes this result applicable, again, is that this strong convergence property is universal. Okay. Let's see if there's any questions. Yeah.
Can you think of it in terms of unit sphere and L2? Regular representation?
So the first problem that you have if you're thinking of infinite dimensional spheres, of course, all the problems make complete sense. But the first problems you have is that maybe you don't have a harmonic map that represents these representations. So this is something weird that can happen in infinite dimension is you impose yourself some equivariance constraints. And somehow, if you try to minimize the energy, you don't get any limit. So it's going to escape at infinity. So even the beginning is not true. Yes?
So in the convergence, what is the hyperbolic metric is converging to? Is it a special one? Or?
Oh, so the hyperbolic metric is the unique one, which is compatible with the conformal structure of S. So in this statement, S is forever a Riemann surface, a surface with a conformal structure. Yeah. And also maybe something that's not clear is that the pullback metric here, a priori, is a metric on S tilde, not S. So, but here I'm going to say the convergence is on S in the sense that because the map is equivariant, well, the pullback metric is going to be also equivariant, invariant by the group action, by deck transformation, and so it descends on the well-defined metric on S. For those of you who know about Kähler geometry, in Kähler geometry there's this famous result of Tien that tells you that if you, under certain settings, you start with a Kähler manifold and a positive line bundle, etc., and you can approximate your metric by pullback metrics coming from maps that are holomorphic embeddings into some CPN. So here, it's a little bit reminiscent of that. You can approximate the hyperbolic metric by pullback metrics via maps that are not holomorphic, but harmonic. let me say a few words about the possible generalizations. Actually, this theorem makes sense for punctured Riemann surface, and it's not just a generalization. Looking at punctured surface really is useful for certain applications. So let me just say that you can replace S by punctured surfaces. The second, oh, that's it actually. Yeah. The other thing I wanted to mention is why is this theorem implying the application? So remember, the application is you start with any hyperbolic surface, a closed hyperbolic surface. There's a cover that admits a harmonic immersion inside a sphere that is almost isometric. Okay. So they can construct a sequence of strongly converging isometric actions with finite image. So the key point here is that such a sequence exists, that strong converging sequences exist. And I'd like to emphasize that right now, so I said that this property is universal. There's a lot of ways to construct sequences that do satisfy this property, but none of those constructions are explicit. None of those constructions are deterministic. And so that's why the resulting surfaces or maps that we get in the end as an application are not also deterministic. Any questions on how this implication works in more details?
Is the finite image is bounded above by a certain number? Or
Oh no, it's going to get bigger and bigger. So you should really think of the situation as you start with your closed hyperbolic surface, and actually the degree, if epsilon goes to 0, the degree has to go to infinity, and it corresponds to, if you think about that, the fact that this finite number, the index, is going to infinity.
So this is the thing that's also controlling the degree of the cover.
Exactly, it's exactly this number.
And are these, in some sense, random quotients? Maybe
in some sense it is, but there was this question of whether or not when you're taking the cover, you can just take a random uniform at random covering space of sigma, and I'm saying that I don't know because the covers that you get here are not according to this uniform measure. Okay, so that's, I'm going to now talk a little bit about organization. So what am I going to do in the next few hours? And again, the idea is to try to talk about things that could be useful for a lot of people. So what I chose to talk about is harmonic maps and minimal surfaces a bit. Something called epsilon regularity and some existence theory. Basically, this chapter, this section, is going to justify the word standard harmonic theory, my standard harmonic theory. So those are very basic tools, at least for geometric analysts, and I think they're very interesting. So the second section is going to be about representation theory. So I know that you've seen unitary representations in this mini school already. But I'm going to talk about certain things that are going to be useful to me, in particular, what it means to be weakly equivalent for unitary representations, what it means geometrically. I'm going to talk about the representation theory of PSL2R. This is also another very classical subject, but somehow it's super useful for us to understand the limiting behavior of those metrics. It's going to come from this thing. And I'm going to talk a bit about strong convergence, of course, which is central in our main results. Then in 3, I'm going to talk about the proofs, how all these elements combined can be combined with each other to give statements like that. And in 4, what I'm going to do is I'm going to discuss a little bit some analogies or relations between these kind of results and other kinds of results. So, for example, there are some vague analogies between the things here with, say, the almost totally geodesic surfaces of Markovitch. So they're also philosophically using random methods to obtain their surfaces, except that instead of random matrix theory, they're using dynamical systems, right, the frame flow. And I'm going to explicitly state some questions also. So I don't think I have time to say more, so I'm going to stop here. Thank you.
Question? What if the target is the real projective space or the complex projective space?
Yeah, good question. So a lot of those things make sense also if you have other target spaces. I have no idea what happens. So the reason why isometric actions on spheres are easier to study is that they directly correspond to orthogonal representations. Yeah.
Question?
So you mentioned we had that conjecture about the 1A optimalities, but is that something that's appearing on that main theorem? Do you look based on that language?
Yes, yes. So it's going to be appearing here already. Yes.
In which part do you use the two-dimensional assumption in both, or?
So in several ways. So first is, as I said, in the existence theory, how do you get a harmonic map already? This first step is much easier for surfaces. The second part where it's used, for example, is I mentioned in the end that there's this result of Lauder and McGee that tells you that there exists a sequence of representation that strongly converge, and that uses that you have a surface group and not some, say, higher dimensional hyperbolic.
Thank you. Many parts. Thank you.
Is what you're using by SL2R representation theory also special?
Can you repeat that?
Is what you're using by SL2R representation theory also special?
Oh yes, actually this is also very special. So there's some use of some specifics of the representations theory of PSL2R, and I do not really know how to generalize that.
Sorry, this is going to be a long question, so I can ask that. Oh, okay, well, if the dimension of the sphere is 2, are the random negative derivatives somehow holomorphic? Like, should we think about this as some form of quantum unique rigidity, or is it completely, if you see what I'm asking?
I don't, but we can talk about that later, but I'm not sure. So it's an interesting question. I'm not sure what happens if you say choose the representations at random, but you force the dimension of the sphere to be 2, to state 2.
Can you allow cusps for your surfaces?
Yes. So I quickly mentioned that, but you can allow your surface to have finitely many punctures. In that case, the fundamental group is a free group, and there's a lot of things that's easier for the end. Yeah.
So you mentioned this result of Brandt that said, like, if you want it to be harmonic plus isometric, then there don't exist any maps into Sn. But then if we can have an equivalence class on the hyperbolic matrix instead of just scaling by constant, but looking at the entire conformal class.
That's also not enough. Oh, so if you allow yourself to rescale what by a constant or function?
The conformal class of matrix equivalent to the hyperbolic matrix.
Oh, so if you stay in a conformal class, but you're not a rescaled hyperbolic metric, then you do have such maps. And that was you have a lot of harmonic maps.
Oh, it's still no uniqueness or nothing like this?
Absolutely not.
Okay.
Okay, let's have coffee. We'll be back in 30 minutes.
Okay.